Welcome to this lesson on the Nernst equation, a fundamental concept in electrochemistry. This equation allows us to calculate electrode potentials under non-standard conditions, which is crucial for understanding how batteries, fuel cells, and many biological processes work. Let's start by understanding the purpose of the Nernst equation. In electrochemistry, we often deal with redox reactions where one species is oxidized and another is reduced. These reactions can be split into half reactions, which show either the oxidation or reduction process. Under standard conditions, where all concentrations are 1 molar and all gases are at 1 atmosphere of pressure, we use the standard electrode potential, E0. But in real-world applications, we rarely have these exact conditions. That's where the Nernst equation comes in. It allows us to calculate the electrode potential under any set of conditions. Now, let's look at the general formulation of the Nernst equation. For a half reaction involving n electrons at temperature T, the Nernst equation is given by E equals E0 minus RT divided by NF times the natural logarithm of Q. Here, E0 is the standard electrode potential in volts, R is the universal gas constant, T is the temperature in kelvins, F is Faraday's constant, and Q is the reaction quotient. To make calculations easier, we often use a simplified version of the Nernst equation that applies at 25 degrees Celsius, which is 298 Kelvin. At this temperature, RT divided by F equals 0.025693 volts. We can also convert the natural logarithm to base 10 logarithm, giving us E equals E0 minus 0.05916 volts divided by N times the log base 10 of Q. This simplified equation makes calculations much more manageable for common laboratory conditions. An essential part of using the Nernst equation is correctly defining the reaction quotient, Q. If we have a half reaction where a moles of A plus B moles of B plus N electrons yields C moles of C plus D moles of D, then Q is defined as the concentration of products raised to their stoichiometric coefficients, divided by the concentration of reactants raised to their stoichiometric coefficients. For this calculation, we use activities which are approximately equal to concentrations for dilute solutions or partial pressures for gases. Solids and pure liquids have an activity of 1 and don't appear in the expression for Q. Let's work through an example to see how the Nernst equation is applied. Consider the half reaction. Silver ion plus 1 electron yields solid silver with a standard electrode potential of positive 0.799 volts. Let's say we have a silver ion concentration of 2.0 times 10 to the negative 3 molar at 25 degrees Celsius. First, we identify that N equals 1, since 1 electron is transferred. Next, we calculate Q. Since solid silver has an activity of 1, Q equals 1 divided by the concentration of silver ion, which is 1 divided by 2.0 times 10 to the negative 3, giving us 5.0 times 10 to the 2. Now we can plug these values into the simplified Nernst equation. E equals 0.799 volts minus 0.05916 volts times the log base 10 of 5.0 times 10 to the 2. This equals 0.799 minus 0.05916 times the quantity log base 10 of 5.0 plus 2. The log base 10 of 5.0 is approximately 0.6990, so we have 0.799 minus 0.05916 times 2.6990, which is 0.799 minus 0.1596, giving us 0.639 volts as our final answer. Let's summarize some key points about the Nernst equation. First, E decreases if the products are favored, meaning Q is large, and increases if reactants are favored, meaning Q is small. Second, always match N to the number of electrons in the balanced half reaction. Third, use the base 10 logarithm form at 25 degrees Celsius for quick calculations. E equals E0 minus 0.05916 divided by N times log Q. Finally, for full cells, find each half cell E with the Nernst equation, then calculate the cell potential as E cell equals E cathode minus E anode. Let's visualize how concentration affects the electrode potential. Here we have a silver half cell with a silver electrode in a silver nitrate solution. When the concentration of silver ions is high, there's a greater tendency for reduction to occur, resulting in a more positive electrode potential. As the concentration decreases, the electrode potential becomes less positive, following the Nernst equation. We can plot this relationship on a graph. As the negative logarithm of concentration increases, meaning concentration decreases, the potential decreases linearly with a slope of negative 0.05916 volts per decade change in concentration for a one-electron process. And that's the Nernst equation. It's a powerful tool that helps us understand how concentration and other non-standard conditions affect electrode potentials. This equation is essential in electrochemistry, from understanding batteries and fuel cells to biological electron transport chains and pH meters. Thank you for watching, and I hope this explanation has helped you understand the Nernst equation and its applications.